All right, good morning, everyone. Let's start by taking a look at your work from yesterday. So if I can just get you to open up your materials to the questions you were working on. These were textbook problems where we were solving trigonometric equations graphically, mainly because you cannot solve these equations algebraically. I mean, I'm not saying it's not possible to solve them algebraically. I'm saying at this level, solving them algebraically is very confusing. It's confusing at any level, actually, because we start to lose, especially when you get to word problems and applications, you start to lose touch with the fact that your independent variable, x or t, is no longer really an angle. It's a time, or a day of the year, or something that's really not connected to a rotation at all. And then trying to find solutions without referring to rotation angles becomes awkward. Anyway, you need to solve these graphically, and essentially what you want to do is set up your x min and your x max to be reflective of one period of the function. So you have to look at the equation of the function and determine the period, which can be found by taking 2 pi over b, so that you can, once you know the period, you can set up your x min and x max. You want to look at the graph horizontally for one complete cycle. In terms of your y min and y max, well, you want to look at your minimum and maximum values of the function. The minimum is going to be your vertical displacement minus your amplitude, and the maximum is going to be your vertical displacement plus your amplitude. And I have capital A for amplitude because if little a, the parameter in the equation, is negative, that's not the amplitude. You need to get rid of it. And we talked yesterday about the fact that, if the minimum value of the function, for example, in this question we're looking at, the minimum value of the function would be 2,000 because the middle of the graph is at 8,000. I'll show this to you visually. The middle of the graph here is at 8,000 because of the vertical displacement of 8,000 in the parameter d. Let me write this down. This is the 8,000. And the amplitude is 6,000. Well, that means that it goes 6,000 above and 6,000 below. So the minimum kind of guideline will be down here at 2,000. The maximum will be up here at whatever 8,000 plus 6,000 is, which is 14,000. So in order to determine your maximum y and your minimum y, I'm talking about for your window settings, by the way, you have to look at the values of a and d. In this particular case as well, since b is 1, because there's a coefficient of 1 in front of your t variable, the period is really 2 pi. It's very strange. Sorry, it's not strange. Something that I was thinking of makes it strange. Don't worry about it. Since it's sine of 1t minus 8, the parameter b, which is the coefficient in front of t, is 1, so your period is 2 pi over 1, your period is 2 pi. In other words, if you want to graph this to see one complete cycle, you're going to set your window settings to be 0 to 2 pi for x. And I do recommend going 0 to 2 pi. And then for y, I don't recommend going 2,000 to 14,000. I would probably recommend going 0 to 16,000. I like to have a little bit of cushion room above the max and below the min. And then if you were asked questions about the specifics, like for question A, if you were asked for the population, it doesn't really tell you what t is. Let's just assume it's days. If you were asked for the population at 10 days, then you would put 10 in for t and look at the location on the graph. If you were asked when is the population 10,000, then you would graph y equals 10,000 and see where it intersects with that function. In fact, I didn't even realize it, but what I've done here, this picture of my graph with the numbers, that's really the answer to 6a. I don't know that I assigned 6. I probably didn't. Okay. But those would be an appropriate domain and range settings for your calculator. All that being said, does anybody have any questions you would like me to go over? Go ahead, Jason.
Just clarification for 13. I didn't know how the formula is. I didn't know where the brackets were.
You didn't know what?
I don't know how the brackets go on.
Oh, yeah. It's, we seem to be very by the book when it comes to brackets and writing things. And then when trigonometry rears its ugly head, we get sloppy. And not just me or you guys, but the text and the language becomes a little more loose. This is saying that the number of foxes, the fox population, is 500 multiplied by the sine of pi over 12t, close brackets, plus 1,000. And I think that answers your question now, right? Okay. The stupid thing about this is there's an operation between the pi over 12 and the t. So really, we should be putting them in brackets. So we can get away with writing something like sine of 4x. We know it's sine of 4 times x. It's not sine of 4, then times x. But when we write something like sine of x plus 12, because we get used to seeing no brackets, we might incorrectly think that that's what they're trying to say, and it's not. As soon as you have that plus or that minus, that's outside of the argument for the sign. Any other questions? Go ahead, Ryan. 9. Okay. So what are we dealing with here? A point on a flywheel. You don't need to know what a flywheel is. It doesn't matter. It's something that's spinning. Okay? It's a wheel of a sort. The height of a point on the flywheel. So we have a circle and there's a point on the flywheel. And this point is going to be a certain height. It doesn't really say above what. But it's a certain height. I'm just going to say it's above some point, maybe the ground or the bottom of an engine part or something. So this is the height. This is your y. And t is your time. We can answer A without graphing it, everybody. Because when it says what is the maximum height, you should understand that the middle of this graph is going to be 15. Because the value of the parameter d is 15. And since the amplitude is 13, this graph will go 13 above 15 to 28. So we've already answered A. The maximum height is going to be 28 meters. Wow, that's a huge flywheel. It's not on an engine, it's on something else. After how many minutes is the maximum height reached? We could probably figure this out without graphing it on the graphing calculator because it's a cosine function. And the coefficient in front of the cosine, A in other words, is positive. This graph will start at the top and go down, down, up, up. So it starts at its maximum height, looking at this, and it reaches its maximum height again in one period. So if we knew the period, we would have the answer to part B. And I can find the period by remembering that for sine or cosine, it's 2 pi over b, and b is 2 pi over 0.7. Everybody, I'm going to go a little off track here. Remember I told you that you could simplify something like this by multiplying by the reciprocal, but I would rather you didn't? That's going to become really important today and tomorrow and the next day. It's better to say, I want to make this complex fraction a simpler fraction by eliminating this pesky 0.7 as a denominator of the denominator. So I'm going to multiply top and bottom by 0.7. What happens here is the 0.7s here and here cancel, the 2 pi's cancel. The period is 0.7 minutes, because I'm looking back at the question, I'm seeing minutes. So the distance, or the time, I suppose is a better way to put it here, between when the flywheel starts at the top and reaches the top again is 0.7 minutes, which is the answer to B. What is the minimum height of the point? Well, if the amplitude is 13, then we can figure out that the minimum height is 13 less than the midpoint, which is at 15, which would be 2 meters. After how many minutes is the minimum reached? Well, again, we don't have to use our graphing calculator to answer this. You can just say the minimum is going to be reached halfway in its cycle. So if it's 0.7 seconds, my graph is not really that great. But remember, it's 4 equal pieces. So this time corresponds to half of the total period. So the answer to D would be 0.35 minutes, half of the period. Now for E and F, well, let's do F first. For F, if you want to determine the height of the point after 1 hour and 12 minutes, 1 hour and 12 minutes is 72 minutes. Does that make sense to you, where I'm getting 72 minutes from? An hour is 60 minutes plus the 12 is 72. You're trying to find the height. Well, you can just go ahead and put that 72 in here on your calculator. So take 2 times pi times 72 divided by 0.7. Take the cosine of it, multiply by 13, and add 15. And you could certainly just string it all through at once, as long as you put your brackets in the correct place. You want to make sure that you are in radians, of course. (13 cosine 2 pi times 72 divided by 0.7. We talked a little bit yesterday. You could go 2 pi divided by 0.7 times the 72. It doesn't matter where you divide by that 0.7. And then I have to add 15. 13 cos looks okay. So about 23 meters. Now, to answer E, you have to look at it on your graphing calculator. And part of me, when I saw F, Ryan, wanted to say, let's do F on the graphing calculator as well, because I knew we had to do E on the graphing calculator. So I'll show you E and F both at the same time. I'm going to enter in for Y the function which is 13 cosine 2 pi x over 0.7, close the brackets on the argument for cosine, plus 15. I'm going to use what I started this little review with today, A and D, to find the minimum and maximum. Well, we already did, right? It goes up to 28. So for Y, I'm going to go 0 to 30. And for X, I want to do 1 period, which we said was 0.7. And if I've done things right, and I didn't double check everything here, but if I've done things right, I should see what we said we should see. And it's working, right? It looks right. So if we go back to F, and I want to know the height of the flywheel at 72 minutes, since I've only gone up to 0.7 minutes, I'm going to take back what I said and say this is not a good question, F, to answer on the graphing calculator. Not unless we want to do this. Go from x, for x from 60 to 80. And you know what? I suspect even then it's going to be, we won't see anything, right? It's going to be a mess because it's going around once every 0.7 seconds, right? Or every 0.7 minutes, rather. So this is going to be a mess, right? It's not going to be helpful at all in answering E, but we can answer F now. You can go trace 72 and go enter, and it's 23.1. Remember what I told you yesterday, the fact that your calculator is having that fit and drawing that jagged diagram, that's not what it looks like. It just doesn't, there's too much happening at once. So now to answer E, and I'm not going to go through all of the work, I'm just going to tell you how we would do it. If you want to know when is the flywheel, when is that point less than 6 meters, then you're going to have to graph y equals 6. And you're going to have to find these two intersection points and look at the x coordinates for each and subtract them to find out the length of time it's in that region on the graph. Does that make sense? Okay. All right, we're going to get started on the next lesson now, which is dealing with identities. We're going to be verifying identities, specifically trigonometric identities, numerically and graphically. We're going to be determining and talking about non-permissible values of identities and working with identities in general. So we're starting off with an algebraic, non-trigonometric warm-up. We have an equation that I've given you, 2x squared minus 23x plus 5 equals 77 minus 5x. We're asked to verify that that equation is true for x equals negative 3. And what this means to verify is that you have to take the approach that you don't know if x equals negative 3 makes it true. So you have to work on the left-hand side of this equation and the right-hand side of this equation separately from one another. We don't put equals here. What we're going to do is just put a line and say the left side is 2 times negative 3 squared minus 23 times negative 3 plus 5, and we're going to calculate what that equals to. I would like you to calculate what that equals to. I want to say 92, but I don't know. Is it 92? So we get 92 on the left-hand side. And on the right-hand side of the equation, we have 77 minus 5 times x, but x is negative 3. So this is 15. Negative times negative is positive. 15 and 77 is 92. Okay, so what we have done is we've basically said that the left side and the right side are equal when x is negative 3. So we have verified that the equation is true when x is negative 3. Does x equals 12 make it true? I don't care if we show any work here. I would like you to put 12 in for x and figure out what the left side would be equal to and what the right side would be equal to. I think it's 17 for both. So the actual answer to B is yes. is it true for any value of x? Well, you know what? You don't know how to prove if something is true for any value of x, but if you can find one value of x where it's not true, then we can answer this question and say no. And I'm looking at this thing and I'm going, well, what's a really simple number to use for x? How about 0? Because if I put 0 in for x, all of the variable terms go the way of the wind, they disappear, and all we're left with on the left side is 5 and 77. So just as an example here, this is actually what we call a counterexample. At x equals 0, we get 77 on the left side, and nope, we get 5 on the left side, and 77 on the right side. So the conclusion we draw in A is that the left side and the right side are equal when x is -3, so -3 makes it true. In B, the left side and the right side are equal when x is 12, so x equals 12 makes it true. But because we found even one value of x that the left side and the right side are not equal, we can answer this question, and the answer to the question is no. Warm-up number 2, we have a different equation. This is x plus 5 quantity squared plus 37, and then it's equal to x squared plus 10x plus 62. I would like you to verify that if you put -3 in, the left and the right side will give you the same thing. Do you in fact get 41 for both? Okay. So, you know, something I didn't write here, which maybe I should. I'm going to go back to number 1. You know, we would probably write left side equals right side here. We would probably write left side equals right side here. And we should probably write left side is not equal to right side here. And when I say left side is not equal to right side in C, I'm saying for x equals 0. And maybe in a more general sense, I'm saying it's not always equal. So there we go. What's going on here? In A here, we can make the conclusion that the left side equals the right side. How about x equals 12? Let's put 12 in for x. I'm sure you guys have already finished this, many of you. I don't know. I lost track. 326? No. Is it 326? Wow, I surprised myself. For both sides? Should be. That's the way I designed the question, I think. And I just forgot what I said. 326? Okay. So what do we conclude? We conclude that the left side is equal to the right side. Now, is it true for all values of x? I'm going to tell you the answer is yes, but you can't prove it yet. I'm going to show you how to prove that that's the case. Because if you keep trying a gazillion values of x and you find it's always true for any particular value of x that you stumbled on, that doesn't mean it's always going to be true for all values of x. Maybe there's some weird value of x that when you put in, it won't be true. But the fact of the matter is, these are always equal. If I were to take the left-hand side of this and simplify it, and this is the basis for everything we're going to be working on for a while, changing the appearance of something so that it's the same thing, but it looks different. We know that x plus 5 quantity squared means x plus 5 times x plus 5. I don't have an equals in here. I'm just working on the left-hand side of this, and I'm going to simplify it. I FOIL this out and get x squared plus 5x plus 5x plus 25 plus my 37. I simplify it, x squared plus 10x plus 62. It's the same thing on the right-hand side. So that would be proving that it's true. There's a difference between putting in a number and verifying that it's true for a number and proving that it's true for all numbers. The answer to this question is yes. Okay? So, any questions with that warm-up number 2? All right. So, when you see the word equation in mathematics, all that means is it's an expression equal to another expression. There has to be an equal sign in it. So what an equation is a mathematical statement that equates two different expressions. They're algebraic usually. They don't have to be, but I want to stick with algebra here. They could just be numbers. Like x equals 5 is an equation, but that's pretty boring. Some equations are identities. This is like me talking about all birds are animals, I'm not a taxonomist, are animals that lay eggs and have feathers and wings. Okay? You'll have to live with that definition. There's probably a more scientific one. But in the set of all birds, there's a subset of birds which are called chickens. Chickens are types of birds. Identities are types of equations. Every identity is an equation, just like every chicken is a bird. But not all birds are chickens, and not all equations are identities. Does that analogy kind of, you follow that? What an identity is an equation that's always true for all of the allowable values of x. And we have to talk about what that means. So I'm going to give you an identity that we're going to look at here. That's an identity. And one of the ways to verify that it's an identity is to use your calculator and put one side in for y1 and the other side in for y2. And then go to our tables. This eliminates the need for us to be plunking around and putting in different values of x. The calculator can do all of that grunt work. All we're going to do is set the calculator up for success by putting in for y1 x squared minus 4 over x minus 2. Now look very carefully on how I entered that. I do need brackets around the x squared minus 4. If I don't, then it's just going to subtract 4 over the other stuff. And I do need brackets over the x minus 2. And for y2, I'm going to put x plus 2. And I would like you to humor me here and go to your table setup and start at 4 for x and go up by 1. Okay? So now when I go to my table, I see that y1 and y2 get the same result for any particular value of x. You know, when x is 14, the left side is 16, the right side is 16. So do you agree that it's true everywhere? Well, we haven't really proved everywhere because maybe it's not true when we go to decimals, but it is true. Okay? Now, if you scroll up, and it doesn't matter if you're in this window setting or not, you will get to x equals 2. And the left side is error, which means it's not defined, which you should know from last year. You can't put 2 in here because then you're dividing by 0. But I hope you agree error is not the same as 4. It's still an identity. As long as it's left side equals right side where they're both defined, then it's an identity. And that's why I've said for all permissible values of x. If there's a value of x that makes one side not defined, it's still an identity. All right, so in our warm-up, 2x squared minus 23x plus 5 equals 77 minus 5x is not an identity, because we found examples of x that made it not true. X plus 5 quantity squared plus 37 equals to x squared plus 10x plus 62 is, I guess I should clean up my English. This should say is not. And the second one is an identity because we've proved it. If you expand out the left-hand side, you see that it's just disguised differently than the right-hand side, but it's the same thing. It just has a different mask on. So, any questions on what an identity is? Any questions about anything we've covered so far? Because things are about to, as they say, get real here. It's going to get complicated quickly. All right, so we are going to look at, well, here are some other identities. Is secant of x always equal to 1 over cos x? Yeah, because that's a definition. Is this always equal to x squared plus 4x plus 4? Well, yeah, because if you expand x plus 2 times x plus 2, that's what you get. Is x squared plus 2 always equal to 11? Well, it's equal to 11 when x is 3. Run that around in your head. When x is 3, x squared plus 2 is 11, yes? When x is negative 3, it's 11, yes? What about when x is 1? No. So it's not an identity. Cosine of x equals a half in certain places when x is 60 degrees, but not when x is 58 degrees. All right. So now we're going to get into the trigonometric identities. Consider this equation: sine of x equals cos of x times tan of x. What are non-permissible values of x? Well, non-permissible values of x result from division by 0. You know, there are other ways we could get non-permissible values, like square rooting negative numbers, but in terms of everything in this unit, if you are ever dividing by 0, the thing that the variable is equal to that results in that division by 0 is not allowed. The math god slaps you on the hand and says, you can't do that. Well, sine of x is never undefined, because sine of x is y over r on the unit circle, and r is always some non-zero number. Same with cosine of x. But one of these, tangent of a rotation angle, is the y coordinate over the x coordinate. Do you see how I switched variables there? The variable is x in the equation, and I'm just using theta, because I have to talk about x on the unit circle, and x on the unit circle is not the x in the equation up here. So where is x 0 on the unit circle? X is 0 at the top of the rotation and at the bottom of the rotation. We've talked about this before. This means that tangent at pi over 2 is not defined, because at pi over 2, it would be the y coordinate divided by 0. And at 3 pi over 2, it's not defined. And these two are separated by pi radians, so really we can write the non-permissible values are x is not allowed to be pi over 2 plus multiples of pi. By the way, these are your locations of the asymptotes on the tangent graph that we talked about, that weird, goofy graph. I don't want you to get held back on this stuff because you're confused about non-permissible values. We're going to keep coming back to them and improving our skills with them, but it's not as important right now as what's going to come. Verify that the equation is true for 40 degrees. So take your calculator, put it in degree mode, find the sine of 40 degrees, look at the decimal on your calculator, and then take the tangent of 40 degrees times the cosine of 40 degrees, look at it to verify that it's true. So tan 40 times cos 40 is 0.642 something. Sine 40, same thing. But I don't think we need to write anything there. It's true. Okay. We're not going to get into this isn't a philosophy class. We're not going to talk about, well, maybe the next decimal is different. We're going to use a bit of common sense. Verify that it's true for all permissible values of x by comparing the graphs of the two. So I'm going to put in sine of x for y1. I'm going to put in tan of x, cos of x for y2. I'm going to go zoom trig, which is zoom 7. Here's sine of x. And then we're going to have a problem. And it's why I don't like graphical verification. The problem is, if they're identical graphs, I can't see the second graph being drawn, right? But I can solve that problem by going back to y equals, and I'm going to do it for the tangent graph, the one that has tangent and cosine, scrolling over to the left of the equal sign, and I'm going to hit enter a number of times until I see that little, what I call the bouncy ball. You could use a thick line, but I'm going to show you why I want the bouncy ball. So now I'm going to graph. It's going to reset. It's going to graph everything from the beginning. So here is sine of x. And watch very carefully when it graphs the next one. It's following the curve. But do you see it's stuttering kind of? It's skipping in certain places? Those are the non-permissible values because that's where tangent is under. So they're the same. I personally just like going to my table to verify something. It's much more, it's less visual, it's more numerical, but it makes more sense. Is that equation an identity? Well, we think so. But that's not really a definitive proof based on looking at your calculator. We can prove it, though, because, and this is a really weird proof. Don't worry about writing this down. Tangent of a rotation angle is y over x. Sine of a rotation angle is y. Cosine of a rotation angle is x. So if you're looking at this identity, and notice again, I got rid of the x's and I'm putting theta. If you look at this identity, on the unit circle, this is y, this is x, this is y over x. You get the same thing. And if I had r's, it wouldn't matter because all of the r's would cancel as well. All right, so now we're going to look at the identities. The first set of identities we're talking about today are called the reciprocal identities, and you already know these. These are defined for you. Okay? What this means, everybody, and this is the important point of today's lesson and the rest of the unit, basically, is that anytime you're doing work, if you see cosecant of theta, feel free to change it to 1 over sine of theta. If you ever see in your work cosine of theta, feel free in the next line to write 1 over secant of theta. You don't know why you would want to do this, by the way. I'm just saying we can change the appearance of things. Okay. I really can't think of a situation where you would want to do this, but if you were working in this unit and you saw sine of theta, you could write this because it's the same thing. And I know the brows start to wrinkle here and you go, well, why would I want to do that? We'll get there. Okay. So you're familiar with these identities. There are also things called the quotient identities. And the quotient identities are called quotient identities. What just happened there? The quotient identities, I lost a page somewhere, are called the quotient identities because they define a trigonometric function, tangent or cotangent, as a quotient of two others. I think you kind of suspected that this first one was always true. Because tangent on the unit circle is y over x, isn't it? And sine is y and cosine is x. And this should make sense to you then. Because if you buy that tangent is sine over cos, which should make sense, cotangent has to be the reciprocal. Then we have these three, what we call Pythagorean identities, because they're proven using the Pythagorean theorem. I will tell you right now, all of these identities that I'm showing you, you never have to prove. And you don't have to memorize them, they're on your formula sheet. So let's talk about this one for a second, just briefly. This is the most famous trigonometric identity. It's one that you're going to see so frequently in your work. Sine squared of an angle plus cos squared of an angle is always going to give you 1. That's because x squared plus y squared is 1 on the unit circle. What does this mean? It means if you are in, I think I'm in degree mode, it doesn't matter. If you are in degrees, and I take the sine of 52 degrees, quantity squared, remember that's going to square the whole sine, not the 52, plus the cos of 52 degrees, quantity squared, I'm going to get 1 without fail every time. Put in 38 degrees, put in negative 11 degrees. It doesn't matter, you're going to get 1. I hope you remember that I made the point earlier that you could always take this thing and change it to this thing because they're equal, right? And I said, you probably wonder, well, why would you want to do that? Well, this Pythagorean identity is a perfect example. You're doing some work, and maybe in the work you're at this stage. And maybe I ask you to simplify that. Look at that question. I'm asking you to simplify that. Right? If you saw that on day 1 of this course, you'd run from the room screaming. Like, what are you talking about? Well, but this in the brackets is 1. Right? It's right here. This is 1. Tangent of theta is sine of theta over cosine of theta, isn't it? Cosecant of theta is 1 over sine of theta. None of the three things that I did, changing cosecant to 1 over sine, this to 1, and tangent to sine over cos, I don't think none of those three things are really conceptually difficult to understand. Look at what happens, though. You're left with 1 over cosine of theta. You're left with secant of theta. This is equal to secant of theta. That's the kind of work we're doing. You want to change the appearance of things to turn them into something simpler. Okay, when you go to your formula sheet, if you take a look at your formula sheet, among other things on your formula sheet related to trigonometry are all of these identities. while you're getting your formula sheet out, I have a little handout that I would like to give you. And in all the work we do over the next part of the course, you need to be looking at your formula sheet. You need to be using your formula sheet. I suspect that what's going to happen today, everybody, is that we're going to get through the examples, and then tomorrow in class, and probably in the seminar as well, we're going to be working on problems. Okay? I do not want to rush through this to finish the examples so that you have 5 minutes to work on it on your own. I would rather go slow. Yeah. There's no quick way to do this. There isn't. Well, there is, but it's a bad way to do it. I think I gave you two. Just throw the other one up here. So on your formula sheet, you have the arc length formula, and then you have all of these identities. You are expected to know the names of them. You'll learn why later, but you are expected to know that the quotient identities are tangent equals sine over cosine, cotangent equals cosine over sine. The reciprocal identities are, well, they're reciprocal identities. You can see there's a reciprocal in them. The Pythagorean identities are the ones that have the squareds. All right, what I gave you is a handout that gives you suggestions for how to solve problems. Okay? So I'm going to be referring to that. Examples continued. Verify that this is true for all values of x. Well, I already did this on the calculator. Did we do this one? I used 52 degrees. Do we need to spend class time doing it? You can trust me, if you put your calculator in degrees and go sine squared of 40 plus cos squared of 40, you'll get 1. So I'm going to say, yep, even though we haven't done it. If you think I'm trying to deceive you, I'm not. Okay, you can try it on your own. Probably something I would take out of the lesson next time. Why is this identity always true? Well, the reason is that on the unit circle, we've defined sine of theta as y, cos of theta as x, and on the unit circle, x squared plus y squared equals r squared, which is 1. So again, in order to explain this, I revert to theta instead of x. We tend to use x a lot, and I wish we didn't, but we do. On the unit circle, sine of theta is y, cos of theta is x, and r is 1. So the Pythagorean theorem says x squared plus y squared will equal to the radius squared, which is 1. Okay. So with example 3, there's a lesson that we're going to be doing probably Friday of this week or Tuesday of next week on proving identities. But I'd like to just introduce you to the concept of a proof to begin with. When you do a proof, you want to manipulate the left-hand side using known identities so that it turns into the right-hand side. Or you want to manipulate the right-hand side so that its appearance becomes identical to the left-hand side. Or you can manipulate them both until they come together to be the same thing. Look at the pink sheet I've handed you today. These are suggestions for you, strategies to try when working with identities. And they are not in a particular order other than for me to say the one at the top is what you usually try first. Okay? And I want to use an analogy. I may have used this with you before. You can't look at this and freeze. It's like you wake up for some reason in the middle of nowhere on a road in the woods and you want to get home. You're not going to get home by standing there. You have to start walking, right? And take a look now at the last point on that pink sheet. The last point says, if things become too messy and cluttered, go back to the beginning and try a different path. So if you're walking and you're trying to get home, you don't know where you are, but the road starts getting narrower, and it starts raining, and it's darker, and you hear growls coming from the bush, maybe you should go back to the beginning and try a different path home. But we always start, not always, but we're going to start with changing everything to sine and cosine. That's my first suggestion on that list. I have 1 plus tan squared, and I'm going to write this as tangent of x quantity squared. When you see what the next step is, I don't think you really need to write this. Now, tangent of x is sine of x over cosine of x. And we're going to square this. So we end up with 1 plus sine squared of x over cos squared of x. When we get to the lesson on proofs, I will tell you there's some extra information we need to add in our work. But I would have no problem with you going from here directly to there. If tangent is sine over cos, tangent squared is sine squared over cos squared. Okay? Let's do the same with the right-hand side. Well, the right-hand side is secant squared, which is, again, I'm going to write something that I don't know you need to write, is 1 over cos quantity squared, which is 1 over cosine squared. So we've tried the first step, the first strategy. Write everything as sine and cosine. So what now? Well, one of the strategies says whenever you have two terms and there's fractions involved, put them together with a common denominator. So this is crucial. We're going to put these together with a common denominator, just like if we had 1 plus 7/8, we would change that to 8/8 plus 7/8 by multiplying the top and the bottom of this by 8 to get a common denominator. So let's do that with the number 1. 1 is 1 over 1. If I want to turn it into something over cos squared, then I have to multiply the top and the bottom by cos squared. I'm putting them with the same denominator so I can add them together. You with this, Grant? And I multiply across the top of this left-hand term and get cosine squared. On the bottom, I have cosine squared. And I'm adding sine squared of x over cosine squared of x. I have a very bad habit with trigonometry of saying stuff like sine over cos. I should be saying sine of x over cos of x. I shouldn't be saying sine squared. I should be saying sine squared of x. Oh, well, we got a common denominator. Just like over here, we would write 8 plus 7 over 8 and get 15 over 8. Here we can write cos squared of x plus sine squared of x over cos squared of x. Let me pull this down. This was the right-hand side. You don't need to rewrite it. You can see it on your paper. I have a question for you. How many of you see that these are equal? And more of you, when I ask questions like that, the goal is as every 10 minutes goes by, as every day goes by, more and more of you will go, oh yeah, it's obvious. This is equal to 1 over cosine squared because this is equal to 1. There's an identity on your formula sheet. When you look at the pink sheet I gave you today, look at the second bullet on it. The second bullet is saying keep your eyes peeled for things you've seen before on your formula sheet. You see sine over cosine? Write tangent if you want. If you see cos squared plus sine squared, I want to say write the number 1 if you want, but why wouldn't you? It doesn't get any simpler in math than the number 1. So now what you would do at the bottom is you would say the left side is equal to the right side, and you have proven this identity. Which, by the way, that identity we've just proven is on your formula sheet. You will never be asked to prove it. This was just a warm-up kind of thing. Any questions with any of the steps in that example? Go ahead, Evan.
Well, since you changed that secant of x squared at the beginning to 1 over cos of x, right? Isn't technically secant of x simpler? So would you...
This is a good point. I'll tell you the only reason why I didn't do what I suspect you're wanting to do is I told you on that pink sheet it says change everything to sines and cosines. Okay? And some people need a rule to live by. If I were doing this, I would have just said, well, the right-hand side is secant squared of x. That's pretty simple. And then when I would have got down to here, I wouldn't be able to write left side equals right side yet until I went, oh, this is secant squared of x because the reciprocal of cos is secant, and then that is equal to secant squared of x. Absolutely. Is that where you were going with this? Yeah. You don't have to do work on both of them. When I give you a new sheet, which is going to be very similar with one added point for proving identities, the added point will be keep your eyes back and forth between both sides and know what it is you're trying to get to appear the same. And sometimes it'll be easier to just leave one side alone and get the other side to match it. Are you satisfied with that answer? Okay. Any other questions with that example? When I said yesterday that in order for you to be good at this, it requires practice, I'm serious, okay? Because there are thousands of different types of examples. I'm going to say I don't want us to worry about non-permissible values with this, okay? So I have a question for you. How many of you see that this is equal to sine squared of x? Okay, that's the goal. The goal is for you to start seeing things that you would be surprised that you're actually in your head. Tangent of x is sine of x over cos of x. So when I'm doing work with trigonometric expressions, this is not a proof. When I'm doing work, anytime I see tangent, I say, well, what would happen if I wrote it as sine over cos? And this is the first point on the pink sheet, right? Write everything with sine over cos, with sine and cos, rather. Tangent is sine over cos. Sine of x over cosine of x is tangent of x, which means that tangent squared is sine squared of x over cos squared of x times, now look up here, please. I do not, well, you write what you want to write, but I'm here to give you the best advice I think is out there. I think this is a mistake to write this. I think it's better to write that. Cos squared of x is cos squared of x over 1. If you're going to be doing operations between a fraction and something which does not look like a fraction, make sure you line up numerators and denominators. Oh, jackpot. We're left with sine squared of x. Questions with that one? Go ahead. yes. This is not something I would have seen. What Sienna is saying is, based on this, sine of x is equal to tan of x cos of x. Am I following you correctly? So therefore, tan squared times cos squared is sine squared. Yes. If you see something that is obvious to you like that, definitely. Okay? We are going to be doing that a lot later, where we take an identity that's on your formula sheet, and rather than try to get the stuff we're working on to match it, we take the identity and make it match what's in the expression we're working on, which is what you just described. Perfect. There's so many paths home here, you know, and sometimes you will go through the rain and the mud, and you will do a lot of extra work, and the person beside you will go, well, why didn't you just do this? You could have just walked through this bush and seen your house. Okay, there can be a quick way to do it. Good. Cosecant theta, secant theta over cotangent theta. So we're going to write everything with sines and cosines. Cosecant is 1 over sine of theta. I'm multiplying it by secant of theta, which is 1 over cosine of theta. Look how I'm doing my best to keep things neatly aligned. Over cotan of theta. Cotangent of theta is cos of theta over sine of theta. And now we come to that thing I've shown you about simplifying a complex fraction. I'm going to highlight here for us all of the pesky denominators that we would like to get rid of. Okay, we have this big fraction. The fraction is 1 over sine times 1 over cos over cosine over sine. I don't want denominators in the numerator of this fraction. So I don't want this or this. I don't want those there. I want something without denominators in the numerator. And I don't want this. I don't want over a fraction. Do not multiply by the reciprocal. It's going to fail you soon. What you do instead is you say, what do I multiply the numerator and denominator by to get rid of all of these mini denominators? And I have to multiply the top and the bottom by sine of theta. That will get rid of the sine of theta on the top, and that will get rid of the sine of theta on the bottom. And I also have to multiply by cosine of theta to get rid of the cosine of theta in the denominator of the numerator. But I have to multiply the bottom by that as well. Now, I have to go back and explain something to you about multiplication, because some people will make a fatal mistake here, and I want to avoid that right from the beginning. This is a multiplication here, here, and here. We are not going to take this sine of theta, cos of theta in red and multiply it by 1 over sine and multiply it by 1 over cos. That's not how multiplication works. If I say, what is 2 times 3 times 4? The answer is 24, by the way. You don't take 2 times 3 and write down 6, and then 2 times 4 and write down 8, and then go 6 times 8 is 48. You only distribute when there's a plus or a minus. In other words, there's a binomial or a trinomial. So the order in which I multiply this mess on the top doesn't matter, which means I can multiply this sine of theta times 1 over sine of theta first. The sine of thetas are gone. I can multiply this cos of theta times this 1 over cos of theta, and the cos of thetas cancel. On the bottom, the sine of thetas cancel. Okay, so now we're at my question that I will always ask. How many of you see that the answer is secant squared of theta? Because all we're left with on the top is 1, and on the bottom we're left with cosine squared of theta. And we go back to, Evan's comment. I don't know if it was cosecant or secant. It doesn't matter. But this thing that the arrow is pointing at, to me, is simpler than 1 over cos squared. And I'm able to do that because secant and cosine of thetas are reciprocals. Questions with that one? Oy. Well, when I see squareds, I think Pythagorean identities. And I think what we're going to end up doing here is what Sienna was talking about. Let's go to our Pythagorean identities, which I am going to guess, because I don't use them often enough to have memorized them, even after doing this for decades. Is one of the Pythagorean identities 1 plus secant squared of theta equals tangent squared of theta? No? Cotangent? 1 plus tangent squared equals secant squared. Gotcha. And these are the only two, those other two Pythagorean identities, the one with secant of theta and tangent of theta, and the other one with cosecant and cotangent. I just never remember. I have to look at them. So that's no good, is it? For this question. I got stuff in this identity that doesn't even match over here. So the other one is 1 plus cotangent squared of theta equals cosecant squared of theta. Is that right? Okay. Actually, we're not going to do what Sienna was suggesting. There's a quicker path here. Cosecant squared is 1 plus cotan squared. Cosecant squared is 1 plus cotan squared. And then we have minus cotan squared of theta. Oh, it's equal to 1. Now, could you have, so we're done with this question, could you have said, if I rearrange this equation for cotan squared, to get that, and put this in for cotan squared of theta up there, would that work? Yeah, it would work. Because cosecant squared of theta minus cosecant squared of theta is 0, and then you have negative 1 minus 1 minus negative 1. No. You have negative 1 times negative 1, which is 1. And what, by the way, I think this is valuable information for you to know as a student learning this. What you think is easy might be more difficult for somebody else, and vice versa. Not because the other person is not as smart or smarter, because they're just thinking differently. Okay. So let's go to our pink sheet. The first suggestion I have is write everything with sines and cosines in terms of trig ratios. Wow, it's already done. The second bullet says, remember to keep an eye out for parts of any known identities. Well, I don't see anything there. I think it would be a step backwards, by the way, for you to change cosine of x over sine of x to cotangent of x. I think that's a step backwards. Right now, we've got sines and cosines. You start introducing a third trigonometric ratio, you might be heading into the rainstorm. Factoring, we haven't encountered that yet. We will in, I believe, E, which we will deal with tomorrow. There's nothing to factor. Oh, if you have fractions being added or subtracted, bring them together with a common denominator. So, what's the common denominator here? I'll do this in 2 steps. What will the common denominator be? if I had 1 over 3 plus 2 over 5, the common denominator is the product of 3 and 5. Only because there are no factors in 3 that are in 5 and no factors in 5 that are in 3. It would be a lot different if it was 8 and... well, I can't think right now. 8 and 14. You wouldn't go with 8 times 14 because they're both already containing a factor of 2. Okay, so, but in this case, since 3 is not a factor of 5 and 5 is not a factor of 3, this would be over 15. The same thing goes here. Our common denominator would have to be 1 plus cosine x times sine of x. For a reason I don't want to reveal right now, you do not want to multiply those things out. Don't. Okay, you want to leave them exposed the way they are. And that means that I need to multiply. You can choose to rewrite this if you like to give yourself more room, or you can squeeze it in, but I need to multiply the top and the bottom of this by sine of x to get 1 plus cosine of x times sine of x on the bottom. And I need to multiply the top and the bottom of this by 1 plus cosine of x. And what I get is sine of x times sine of x over our common denominator plus cos of x times 1 plus cos of x over our common denominator. Now, for reasons that, again, I don't want to explain right now, don't multiply out the bottom, but multiply out the top when you put them together. On the top of this entire fraction that is over 1 plus cosine of x multiplied by sine of x, on the top of it, we have sine squared of x plus... so the sine of x times the sine of x written in brown gives us sine squared. Plus, I'm going to expand this out and get cos x plus cos squared of x. I have a question now. Well, first of all, any questions with that step? How many of you see that this is equal to 1 over sine of x? Well, so nobody this time, and that's fine. This equals 1. The sine squared of x plus the cos squared of x doesn't have to be written right beside itself, those two pieces. So what we have on the top is 1 plus cos x, and on the bottom we have 1 plus cos x multiplied by sine x. So the entire top cancels with the 1 plus cos x, and you're left with 1 over sine x, which is cosecant of x. So this is what you're doing in this unit from now on. You're taking, quite frankly, a complicated expression and you're using your mathematical skills to turn it into something simpler. I mean, that whole expression is just cosecant of x. And that is a multiple choice question. Sine of x over 1 plus cos x plus, I might even write cotan here in the question, but plus cosine of x over sine of x equals a, b, c, d. Sine of x, cos of x, secant of x, cosecant of x. So we are going to finish this lesson tomorrow. I would say to you, though, that, oh, was that the last question? Okay, so we're going to practice on this tomorrow. I would say to you tomorrow, to really drive the point home, take a look at some of these questions. I wouldn't even start with 1, 2, 3, or 4. You know, can you, we haven't really talked about factoring, but can you, with, say, for example, number 6, can you simplify these expressions? They look intimidating. But you need to practice some of them. Do a few. Try a few. Don't just go home and shut your brain down. And then tomorrow we're just going to spend 80 minutes. Is tomorrow our seminar as well? It is. So tomorrow we got lots of time. This is a 2-day kind of thing. Because before we move on to the other identities, like the double angle and the sum and difference identities, we got to be as solid as we can with this. Okay? It'll be worth our time. So try a few. Tomorrow we're going to be working on them anyway.